Thank you. My afraid my French is terrible, so I'm not even going to try. So first talk of the day in English, I think. Thanks. So today I'm going to be talking a bit about etcd, this project we work on at CoreOS. I've been at CoreOS for a couple of years. I'm now based in Berlin, and I've spent a bit of time hacking on etcd. So first I want to talk about why etcd, what our motivation was for creating it at CoreOS and why we work on it, and why it might be interesting to you if you're looking to deploy things in containers at scale, particularly using some of the software that we've already heard talked about this morning. The first motivation for us was that, with this fleet of servers, we want to provide upgrades and we need some way to coordinate them because, if you have your fleet of servers and suddenly they all upgrade and restart at once, or all your applications restart at once, then you lose availability in your servers. Whether you're running in containers or virtualization or whatever, you lose availability. So the first kind of goal that was driving us to create something, or the need for something like etcd, was that we wanted a way to coordinate things within the cluster, to coordinate upgrades. And so what we needed was a reboot lock, basically, so that we could have a semaphore in the cluster where when one machine needs to reboot, it can take a lock by decrementing a semaphore, it can reboot, and then once it's come up successfully, then it can increment the semaphore, sort of unlock, and allow other machines to reboot. And in the meantime, while it has that lock, no other machine is able to acquire it, so no other machine can reboot. So what that looks like, for example, in this case, we have a simple sort of cluster with a semaphore lock of 3. When the first machine wants to reboot, it reaches out to the semaphore and sort of decrements it and taking a lock, taking it down to 2. 2 more machines do the same thing, which takes the semaphore to 0. So at this time, there's no more machines that are able to take any locks on that semaphore. So it means if another machine comes along to try and reboot or something like that, it's unable to do so. It's just going to hang. It's just going to wait. Meanwhile, our first server can reboot, come up with a new software, and then it's going to increment and sort of unlock, allowing the next server to proceed safely. So we can guarantee that at most only 3 of our systems are going to be out of action at one at one time. And then eventually, hopefully we've now done this sort of safe rolling upgrade of updates across the cluster, and now all our machines are running the latest version of the software. The second sort of main motivation for etcd was somewhere we could store application configuration. So, in this world where all of our servers, are running software in containers, and all the servers are supposed to be sort of, interchangeable and software can come and go at any time, we want somewhere that we can trust to store application configuration in our application that might come up on any server. And so, we want sort of a centralized store for that, but we need that to be safely able to be used by multiple users, so that when an application starts or restarts, it can load the configuration from the server. But more than that, we also want to be able to do dynamic updates. In this dynamic container world where we have applications running anywhere in the cluster, we want to be able to push out configuration changes without having to go and manually change the software that's running. So we want our config store to have some mechanism to be able to write an update dynamically to containers or to applications that are that host their configuration in that store. Of course, this makes it sort of a single point of failure. If all of our config is in this one store, then it's absolutely critical that it's there for our application's life, to be running. But that means that we need some kind of service that's going to be highly available and provide us some sort of safety guarantees there. So far, based on those 2 sort of key requirements, 2 key goals, that drives sort of 3 main requirements that we would want from this kind of service like etcd. The first is that strong consistency, so it needs to support multiple potential writers and readers, and it needs to support some kind of primitives to do locking, so that one application or one server can take a lock and know that no other server will be able to take it at the same time. The second, as we just touched on, high availability is very important because if we're relying on it to host our critical application configuration, it just needs to be available. It needs to be resilient to server failure, to network partitions, to other disruptive events that happen in our cluster. And then finally, we want some means of pushing out configuration updates. And another way to express that is that the store should be watchable, which means that a client can sort of monitor a particular location in the store, and then when there's a change, it will receive an update that's pushed out by the store. So trying to reframe this in terms of the famous sort of CAP theorem, which talks about limits that are placed on what properties distributed systems can have. So the CAP theorem famously says that a distributed system can, of the three properties of consistency, availability, and partition tolerance, that any system can only really choose two. For something like etcd, we want it to be a CP system. We want it to have tolerance to any partitions or sort of network failures, and we want to guarantee that consistency because locking is so critical. And so we're willing to sacrifice potentially some availability. There might be a failure scenario where it's going to be unavailable, but we haven't sacrificed consistency, and generally we haven't sacrificed partition tolerance. And so breaking it down to what this looks like in sort of implementations, we want something that looks like Paxos, which is sort of one of the canonical implementations of an algorithm that provides something like CP. So this is a common problem. This is not something that that we're the only people to have solved or anything like that. Coming back to sort of Google that was being talked about earlier today, all of their infrastructure in some way or another kind of boils down to Paxos, relies on this Paxos implementation. So a lot of the core services like Chubby, which powers their higher level services like Bigtable, their distributed database, and GFS, their distributed file system. Those rely on Chubby to do their operations, and that in turn uses a Paxos implementation. Likewise, Spanner, their global distributed database, relies on a Paxos implementation, and Borg itself as well uses something similar. So we see that this is a common solution underlying a lot of these distributed systems in sort of the cloud native world. And then even looking at other providers and developers too, in Amazon we see that what powers EC2, it's a bit secret, but we do know that that they use a similar kind of thing, a replicated log powering EC2's data system. Microsoft, similarly, they use a system called Boxwood. And then finally, the thing that people in the open source community would be most familiar with would be Zookeeper in the sort of Apache or Hadoop ecosystem. So underlying a lot of Apache projects, like Hadoop and like things like Mesos, they can rely on Zookeeper, which is an implementation of a similar replicated log system. But at the time, so when we were thinking about something like etcd, as I said, the main solution out there in the open source world was Zookeeper, but that didn't really work so well for what we were trying to do. We're trying to build this sort of new world of cloud native apps where everything's very well compartmentalized. It's sort of easy to deploy, easy to sort of reconfigure in this sort of dynamic cloud native world. And Zookeeper didn't really have a lot of those necessarily have a lot of those properties at the time. We also want in a cloud native world we want things to be have clean APIs that are easy to use and implement. And again, that was not something that Zookeeper provided. So CoreOS, our whole sort of mission at the moment we're talking about is Google infrastructure for everybody else, Giphy, providing a lot of those kind of systems that Google uses internally in the open source world. And so that's where we came up with etcd, which we think is a much sort of simpler system than something like Zookeeper, but still provides you all those those properties that you need that we talked about, around consistency and partition tolerance and safety. So etcd is it's one of our, probably the most popular project from CoreOS. There's a very healthy community, a lot of contributions and users from a lot of other big companies as well, and widely used by open source projects. And then etcd, it really forms like the kind of cornerstone of a lot of these big cloud native sort of container oriented systems. So for example, obviously Kubernetes, etcd is very, very important part of Kubernetes, as I sort of touched on earlier and as I'll talk about a bit more later. Cloud Foundry's Diego, which is another, another system for sort of orchestrating apps and running them in contained ways, uses etcd pretty heavily. There's some different software-defined networking systems like Calico that, or Flannel that use etcd to coordinate networking between containers. And then even the recent, Docker Swarm Kit announcement, which you probably heard a bit about, that uses a lot of the components of etcd internally to provide these sort of safety guarantees and do these distributed operations. So etcd, finally, we're sort of getting to what it is. etcd, it's a key value store. It's something where you put keys and you put values into it, and you get values back out of it. But more importantly, it's a fully replicated key value store that provides these properties of being highly available and providing consistent operations. So as with any key value store, it provides the sort of basic operations of being able to put a value to a particular key, and to be able to retrieve it out again, and then to delete it. So in this case, we're just simply putting to the key foo, we're just putting the value bar, and then at any point in time after that, we're able to get that value back out. We're able to delete that value. Where it gets a little bit more interesting, so in that case, you could just think of it as any key value system like Redis or Memcache, pretty basic operations. Where it gets more interesting is with something like a watch operation. So I mentioned earlier, that's how we can provide dynamic changes. So in this case, if a client does a watch operation on a particular key, foo, then the client will receive sort of a streaming record of all of the changes to the value at that key. So if any other, at that point, then any other writer can make a change to foo, and the first client will be notified of that change in close to real time. And then getting to one of the more sort of critical primitives that etcd provides, it's this CAS operation, a compare and swap operation. And so that provides you this atomic way to do a mutation operation in etcd and guarantee that it's atomic, that it's not going to conflict with everyone else. And so the basic, for those of you not really familiar with compare and swap, what that basically means is in this example, we're telling it, okay, we want to put a value into foo, and the value is actually bar 1, that new value on the right. But at the time that we're putting it, we expect the existing value at that time to be bar. And in that way, we can guarantee that we're doing the exact operation that we think, and that in the meantime, if someone else changes that key to a different value, then we know that operation is going to fail safely. So in that way, we can prevent conflicting writes simultaneously to the data store. There's a demo. I'm not going to do a demo today because we don't really have enough time, but there's a demo up on the web at play.etcd.io where you can, it's a great demo of being able to spin up an etcd cluster and sort of test different failure scenarios and see what happens. So you can take nodes out of the cluster, you can fail the leader node in the cluster, and you can see how etcd responds. And this is all working on a real etcd cluster. Another really important part of etcd is sort of the operational side of things. So looking beyond, the actual key value API it exposes, like how as a systems administrator or a DevOps engineer or whatever, you can deploy and operate etcd. And there's a few, really important features here that we provide and focus on. The first is around runtime reconfiguration. So as I mentioned, this is an issue we had with Zookeeper back when we were first sort of designing etcd, in that it was very, very difficult at the time to dynamically change the cluster. So the Zookeeper cluster had a very static configuration, like it must run on these 5 nodes, and it was very difficult to change that. With etcd, we provide an API to do very deterministic changes and controlled changes of the membership of a cluster. But it means you can, safely change, where your nodes are running if you need to. If you need to migrate a particular etcd node to another server, you can do that in a safe sort of programmatic way that has all the safety guarantees that the core etcd implementation provides. The second operational feature is we can do a simple sort of point-in-time backup of the entire database that etcd is keeping, very, very simply, and then that becomes quite easy to back up in the case of any kind of hard failure. And then finally, we spent a bit of time adding a lot of instrumenting to the core etcd code base to expose a lot of metrics about what etcd is doing and how it's performing using Prometheus exporters. And so that allows the operator again to have a lot of insight into what's happening in the cluster, why things maybe are taking a bit longer than you'd expect, all these kinds of things, how active the cluster is, all these sorts of things. Looking forward, so far I've pretty much been talking about what we call etcd v2, which was the first sort of major release of etcd a couple of years ago now. But for the last year, we've been hard at work on the next generation, which is sort of etcd v3. And etcd v3 is coming very, very, very soon. The milestone on GitHub was actually closed just a few hours ago. So why are we doing etcd v3? There's a few main reasons. The first is that it's just going to provide better performance. etcd2 already performs pretty well, but we know it can be a lot better. We have a lot of ideas that we've worked on in etcd3 to make it scale humongously. Scalability is really important because etcd is relied on critically by these systems like Kubernetes, like Cloud Foundry, like SwampKit, and we want to make sure that etcd is never the bottleneck as these systems look to scale to sort of tens of thousands of systems. Another part that's kind of related to that is sort of efficiency with the APIs. So etcd, historically v2 has used this a JSON HTTP API. In v3, we're moving to a new gRPC-based API, which has dramatic sort of efficiency and performance improvements. So if you're not familiar with gRPC, it's an RPC protocol initially sort of developed by Google, but it's all open source now. It sort of inherits from a lot of their learnings with their internal RPC systems. And so it consists of a serialization format, protobuf3, which is a much more compact and efficient way to serialize data than JSON, which obviously goes to just text. And then for a transport, gRPC relies on HTTP2, which gains a lot of great, cool efficiency improvements like pipelining requests over a single connection and all these kinds of things. So we're trying to take advantage of all that with the etcd v3 API. And we're also sort of taking the time to expose some new operations with the API itself. So etcd v3 is going to expose what we're calling a multi-versioned store, so multi-versioned API. So in this case, we're sort of putting a value to a key, right? Putting bar to foo, and then putting bar1 to foo, and then putting bar2 to foo. So we're just updating the value over time. And after you've done these operations, if you just do a simple get operation, then you'll get the last value that you set, bar2. But now with v3 API, we're going to extend the get sort of API to be able to get a particular version in that history. So in this case, we do a get, but now we've introduced this parameter 1 to saying that we want the first revision of that key, and now we can actually go back and get that value from a previous point in time. So we can, in this way, we can safely go back and look at historical events that have happened in etcd, which provides a lot of, allows for a lot of kind of powerful features on top of that. The next big feature in the API is an extension of that sort of compare and swap operation I talked about earlier, and it's what we call a mini transaction. So if you're familiar with other databases, it's similar to a transaction there, but we call it a mini transaction to be clear that there's quite a limited scope of the things you can do, but it still allows for some really powerful use cases. So in this case, a mini transaction consists of a few different branches you can see here. The first is like a conditional operation. So basically we're saying, if these conditions pass, then we're going to do this, then we're going to do the following thing. So in this case, we'd have two compare operations in the if. So if the value of this particular key, is greater than bar, and the version of this key is equal to 2, if those two checks both fail, then we're going to do this operation, which is putting the key OK to the value true. If the checks fail for any reason, then instead, so for example, if the value foo is less than bar or the version has increased, then instead we're going to put false to this thing. The really nice thing about this is it allows you to do to now act on multiple keys potentially at once, which is a long requested feature request we had for the etcd, but we were never able to achieve it with the primitives that the v2 API exposes. But now we can do that in a safe way with the v3 API. And then finally, some of these use cases that we've always had for etcd, but people would need to sort of write their own logic around them. We're sort of trying to expose them natively, either in the API or in tooling that we're providing with etcd v3. So in this example, we're actually created this concept of a lease, which means that it means that a client can actually take a lease can actually register itself as sort of owning a certain key in the database for a set period of time. So in this case, we create a lease for 15 seconds, and then the client's going to put something to the key foo, associate it with that lease. And what that means is that the client then sort of owns that key for the next 15 seconds. The client can do a keep alive, can sort of refresh this, and as long as the client's alive, it will continue to have ownership of that key and keep asserting that ownership. But then, if the client dies for any reason, after 15 seconds, that lease is going to time out, and then other clients, are able to see that and to take over that foo. So that's quite a powerful primitive when you look at things like leader election. If you want to guarantee that you just have a single leader in a cluster, they can use etcd and use a lease on a particular key in etcd to provide that safely. The next thing that's pretty interesting with etcd v3 is doing a streaming watch. So as I mentioned, you can set a watch on a key, and you can get events that happen on that key. And this can happen, totally streaming over the v3 API. In this case, we're just doing an infinite for loop, just sort of coming back over every single event that's happening over that stream. We can act on every event. And then, I mentioned that we want to provide this, we really focused on the primitives of the API to make sure that things are quite easy. And this is just to give you an idea, a rough idea of comparing it to similar sort of recipes being implemented with Zookeeper. So Curator is a library that was developed at Netflix because they make a lot of use of Zookeeper to provide a lot of these primitive things like a mutex or like a leader election and different queues. These basic sort of structures and operations that you would hopefully that you would want from a system like etcd. You can see that in etcd with the v3 API, these are all actually very, very simple to implement using the primitives that we have. Whereas with Curator, it takes considerable greater amount of sort of logic and code to implement these operations. We think this is important because it means any simpler system is sort of simpler to understand, simpler to debug, and there's fewer areas for things to go wrong. So I mentioned, talking about scale a little bit, I mentioned that, in V2, so it worked pretty well, and we've sort of seen it being used for machine coordination, maybe up to the order of thousands of machines. But, with etcd v3, we're sort of shifting that focus from, instead of being like a machine-oriented, we want to think about more in terms of containers and apps. And we want to orchestrate in the order of millions of applications and containers. Because, these new clusters that we're moving to, running apps in containers opens up the ability to run, many more microservices at a much larger scale. I've got a few minutes. I'll talk a little bit about performance. Here we sort of looking at Zookeeper, comparing the sort of performance of a few sort of popular key value stores, distributed safe key value stores that provide these properties. Here we're just looking at sort of the number of requests per second that's sort of able to be sustained by these different tools. Zookeeper is sort of they've been heavily optimized over many years, and so it's still sort of the leader in this space. And here we see sort of etcd2 is sort of doing okay at around 40,000 keys, and then sort of console is doing all right as well, but a bit lower down. But as you can see with etcd v2, we're still quite a way behind where we'd like to be, which is sort of Zookeeper is the current sort of benchmark for this sort of performance. And there's a few reasons for this that we sort of identified working on etcd2 and that we're looking to fix in v3. The first of these is that every time that there's a snapshot, which is when we take a copy of the store and save it to disk, there's a severe sort of performance degradation. We see that the number of requests per second that etcd2 can sustain just drops right off. So that's something we want to do about. When that performance degradation happens, what you get is you get a leader election because the etcd cluster always needs to agree on a particular leader, and if that leader suddenly the performance suffers terribly, then the other nodes in the cluster are going to think, oh, maybe that leader is suffering, maybe we need to elect a new one, and so while that leader election is happening, you lose all availability to be able to do operations in the database. So, how does Zookeeper handle this? Well, when they do a snapshot, when they write the state of the database to disk, they do it in a non-blocking way. So that's something we look to introduce in v3. Then they also have a bit more efficient management of memory. They do some pretty interesting things with the way that they manage the memory in the JVM. So in Zookeeper, you can see the performance generally is much higher. But you can still have leader elections being triggered when a snapshot occurs. I'm going to move a little bit faster since we're running a bit out of time here. And then the other interesting thing, when comparing performance to something like Zookeeper is that since Zookeeper runs on the JVM, when a garbage collection event happens in the JVM, you also see a severe degradation in performance. With etcd v3, we've actually had the ability to sustain a much higher sustained performance. Here, comparing sort of directly against Zookeeper, we can see that there's similar performance. etcd is a little bit lower in general, but it's much more consistent, much more predictable, and there's no pauses from GC as you still see with Zookeeper clusters. And then looking forward to sort of memory usage and how that's changed a bit, we're seeing a dramatic improvement from V2 to V3. So we've significantly changed how the data is actually stored and represented, and minimized the overhead from each of these keys. So in this case we have 2 million keys. In the etcd version 2, there's quite a bit of overhead associated with every one of those keys, which means it ends up using quite a lot of memory. In etcd v3, that's almost totally obviated. So now we're down to very low memory consumption. I want to talk a little bit about reliability, and why this is so important. So, 99% reliability at small scale. If you just got a cluster of a few servers, that's pretty easy. Since failure is infrequent, and when it happens, a human can restart a server or something. It's not a big problem, not a huge problem. But as you start to get to clusters of thousands of machines, failure becomes more and more likely, since the more machines you introduce, it's more likely that any individual one of them is going to fail. And so we have to start thinking about this as not something we can deal with as at the human level, but something that needs to be automated. And we need the systems that provide the cores of these distributed systems to be very, very reliable. Sorry, we're right up on time, so I'm going to probably jump ahead to the end and maybe take some questions. I'm very happy to talk about this in any more detail at any other time today. But yeah, we have a few minutes if anyone has any questions about anything I didn't cover. And I'd be happy to also go over the rest of my slides with anyone after the talk. Any questions? Yes.
How strong etcd is stuck? Maybe not a good word, that with CoreOS. Is it strongly integrated, or it can be deployed?
Sure. So the question was, how strongly integrated is etcd with CoreOS? It's used in most of these systems I talked about. It's used outside of CoreOS itself. So we use it, we ship it in CoreOS because it provides some of the things we need. So it provides that guarantee about doing upgrades. So that provides that locking service. So it's part of CoreOS. But the etcd project you can go download and run on any Linux, Mac, Windows system. It's not integrated with CoreOS. It's not tied to CoreOS. And then some of the etcd code bases used in these other projects, like SwarmKit, for example, that uses a lot of etcd. It just doesn't actually run the binary. But any other questions?
Donc s'il n'y a pas d'autres questions, on va passer donc à la conférence suivante, qui est William Hoffman de chez Red Hat.